Okay, in this video, I'm gonna talk about object detection problem. In the first look, object detection maybe it's not very relevant to vision, but I assume this is just like a preliminary step of segmentation problem, uh, finding an approximate boundary of an object rather than a precise arbitrary boundary. Uh, Hence, I would like to look to this part as well. Now, object detection is finding a bounding box around an object to segment. Okay. Now, therefore, I'm going to talk about three algorithms in a way. Faster RCNN is one of the famous and most preferred algorithm. I would like to try to explain as much as I can in the as a first example. Uh, First of all, I'm talking about a two-stage object detector. Please note in the very beginning that from one point, from the input of the black box, the neural network system, I'm inputting an image, color image, and at the end of the output of the system, I'm trying to obtain some coordinates and some object IDs. Therefore, when I first hear about these things, I really find it very impossible inserting pixels from one side and obtaining coordinates from the other side. But these systems, relatively 6-year-old right now, and they are getting more and more mature and doing uh, such things, such coordinate regressions or many other regressions in a very successful way. This is one of the very famous techniques, starting with RCNN, then fast RCNN, and this is the third version, faster RCNN. The idea is again, you have some image inputting from here. There is a convolutional neural network converting the data into a different domain, and it is the semantic information is obtained with some features. Now, at this point, this feature map that we obtain at the end of the first layer, it is the first point where we start regressing, proposing some regions, object regions, without names. Okay, we are just talking about, we are trying to obtain some proposals, and those proposals will be in a second stage. This is the second stage, this is the first stage, and this is the region proposals. And after having those region proposals around the image for some particular objects, we will try to find a particular object at the output at the end of the second stage. Now, let's go step by step. An input image, there is a CNN, this CNN is this CNN, and then I'm talking about a feature space where I'm going to use these features to be able to propose coordinates. Now, a few tricks I have to mention here. First of all, although we are finding arbitrarily shaped bounding boxes, squares, or some longer ones or wider ones, there is a concept of anchor. Okay, anchor is a predetermined set, like 6 different types of rectangles, where you just try to obtain, you are trying to estimate one of the anchors. And those anchors are like squares or longer rectangles or wider rectangles. And what we are doing is we are having some prototype bounding boxes before we estimate the coordinates. Therefore, we need this anchor concept, prototype concept, to be able to estimate some region proposals directly from image colors which are passed through some CNNs. Okay, therefore we have at the end an image is converted and downscaled to 20 by 15, for example, and each of these 20 by 15 has k different anchors. And what we're gonna do is we, for all these k anchors, we will try to estimate 4k coordinates like the center and width and height, or you can have it like left hand, top left and bottom right, but four coordinates at the end for a rectangle to be defined. Therefore, we are estimating the Bax transforms, and in the meantime, for every such anchor, like 1, 2, 3, 4, 5, 6, all of them, you are asking or you are trying to obtain the objectness measure. Therefore, what I'm trying to obtain here is an objectness measure, and here for every such anchor, we are trying to say the coordinates. Therefore, in this way, I have obtained my proposals, and we will just sort our proposals based on this objectless metric, and the top 100, a few hundred proposals will be your hypothesis going to the next stage. Now, please note, while I am, for example, finding the objective score or coordinates of this particular one, anchor one, this narrow, longer rectangle, only for this one, I have used the whole image, and the features here are basically utilized to obtain that result. Now, once we go to the second stage, okay, once we go to the second stage, only we will run for the proposed regions, not the whole image. As in the beginning, we used the whole image for proposing regions. Now I'm going to use only those proposed regions, but obviously using these features already obtained here. And the concept is you need a bounding box region of interest pooled by this grid cells. And we have to snap them. In other words, we have to make a tight bounding box in such a way that, therefore, since this is our 20 by 15 output layers, all of them have some features inside. Now you have to just put these things, put this estimated, hypothesized bounding box onto the grid cells in such a way that we will just snap it, we just exactly fit uh, some of those features. Therefore, inside every hypothesis, there will be integer number of features, and those features will be utilized by this extra convolutional layer here to refine our estimation of the bounding boxes. Therefore, we have some initial a few hundred hypotheses, but for every hypothesis, I'm also doing some refinement about the coordinates, and also through a classification laws, whether this is a cat or dog, I have to also classify this information as well. Therefore, what we are doing here is in two stages, we are able to talk about the bounding boxes. We are regressing the bounding boxes by the help of some region proposals and using the same features in the second stage in those hypothesized region of interests. It is a really fast algorithm, and refined bounding boxes can also be obtained. Okay, now about object detection, one other famous technique is feature pyramid network. It is not a single algorithm. In fact, that's the concept being utilized in many of the algorithms. Feature pyramid network is simply a way of using your CNNs, and especially for the case with small objects, obtaining multiple feature layers is a disadvantage, because we go to multiple feature layers to capture semantics, to obtain weave invariance, to be able to detect any object in a much better way. We need multiple feature levels, but we have to pool. But that kind of pooling is basically making us getting a small amount of details. Therefore, what we are doing, especially for the small objects, is obtaining both feature pyramids, image pyramids, and the feature pyramids together. In fact, for a long time, people were using these concepts. In other words, we are having an original image, low resolution, low resolution, low resolution, and in the meantime, you have some features here. Also, those features are getting smaller and smaller. And what we are trying to do here is either using an image pyramid and obtaining the features in a downscaled way, or starting from an original image, as typically in CNNs, we can again make a down sampling through pooling and making your predictions at the top layer, which has lots of invariance to different effects. Here, maybe you can have multiple predictions here for every layer, but this is predicted from here, obtained from here. In other words, I am using image pyramid levels directly obtaining the feature at that resolution. Here I got from this high resolution, and I am feeding this information to the next, this information to the next. Therefore, a knowledge feature space information is propagated through this feature pyramid. And at the end, maybe you are making a prediction, which is a very reliable prediction because we have the invariance in the top. Here, another technique, this is a third technique people typically use. You can do this thing, but in the meantime, making predictions at each layer. Please note this is relatively good resolution. Therefore, small objects can be still determined. Now, and as a solution, this small object detection problem, this final thing is FPN. This is feature pyramid network concept. You go in this direction. From the original image, you obtain as a typical CNN, having pooling and getting narrow and narrow and decreasing the resolution, obtaining semantic information here, localization here. The trick is you come down from here. By the help of the other layers, you will try to obtain better and better resolution back in the feature space. This is your original image space. These are features. And then from here, from these low resolution features, by the help of the previous layer, okay? And what I mean by the help of is you have this, for example, you get this and you have a one by one convolution at this stage, and this one down coming is you basically increase by 2 and you just merge them. Therefore, the high resolution coming from here, this is a high resolution, this is a low res, but this is an upsampling here. By the help of this previous information coming from this layer or this branch, you are able to obtain relatively more reliable features in the correct locations, plus which is also supported by semantic information which is coming from the top. Therefore, which is called feature pyramid network, and this feature pyramid networks are quite useful, and many algorithms at the end prefer to use this kind of a strategy while they are working to make predictions about objects. And those predictions are independent. Therefore, here you make a prediction, you make another prediction, maybe a small object, and you make a prediction. This is the best resolution that you have. And for all these predictions, hopefully either small objects or large objects, both of them can be detected. As a final algorithm, I would like to talk about YOLO. YOLO is you look only once, is the abbreviation of you look only once. That's a single stage detector. Previously, please note I have a first stage as a region proposal. The second stage was in every region they are finding the corresponding objectness and the coordinates. Here we directly go and try to estimate from an image of this resolution through such a network where you have a CNNs with different filter sizes, and you come down to here to 7 by 7 grids, and 5 bounding boxes per grid cells, anchor boxes as before. Okay, and for every anchor box, 4 coordinates and 5 objectness scores. Okay, these are saying that are you an object or not. And finally, we all do these things for C different class, and it has also regressed these probabilities. Therefore, what we are doing here is, again, directly from the data, using the concept of anchor frames and a low resolution grid, we are regressing coordinates, okay? And also some objectless measures and class probabilities. Therefore, this is your 7 by 7, and this is, for example, this is projecting this one or that one, 5 of them here, and in the meantime, it also determines class probabilities. Dog class is blue, for example, and then among all these things, you make your final decisions based on your confidences, okay? And you say that, for example, I carry this one to here, and this inside there is the dog class, and you basically draw this bounding box and assign it to the dog, okay? Compared to faster RCNN versions, using typical training data, uh, it is frame per second is 3 times faster with respect to faster RCNN. But in the meantime, please note mean average precision, which is indicating how correctly you are estimating your objects, slightly smaller value. Therefore, YOLO is slightly doing less, but in a much faster, 3 times faster with respect to one of the best object detectors, faster RCNN. Here are some typical results I would like to note. Please note it's saying bird. This is going, I think it's airplane, if I'm not wrong. Obviously, it's wrong, but think about a machine is doing these things, and these are some typical results. Now, object detection was an approximate way of making segmentation of the objects. Now it's time to talk about segmentation techniques using deep networks.